Hello, my name is Nick Friedl. In this presentation, I will talk about dealing with large numbers of welds within limit and an efficient way to analyze large welded structures. For motivation, I have prepared a simple example, which is a curved beam with a box section, and one of the webs is removed, so we can see the 6 ribs inside of the beam, and each of the rib is welded to flange or web by, let's say, a double-sided fillet weld, but the point is that we have lots of repeating welds, and the question is how can we define them and analyze them in an efficient way, because in this case here we have like 3 welds per rib and 6 ribs, so this would give us 18 welds just for the connections of the ribs to the rest of the structure. And in limit, actually, you can define them all in one step. On this slide, you can see stresses and deflections on the beam. So what I did is I just introduced a vertical load acting on the left end of this cantilever structure, and we get the bending moment and higher stresses here in the curved area. Okay, so just to point out the overview, I'm going to explain generating weld sets from properties. I'm going to talk about the automatic definition of setups and the multi-edit of setups to define larger numbers of welds in one step. So the first thing is to start limit, and I will import the model. In my case, it's an Abacus input deck, and I have to use the file browser, and this is the file I need. So here it is. We can remove the element edges so we get a better impression of the structure. I can remove this flange. It's in one of these element sets, this one. I can hide it, and now we have visibility to the ribs. We can see that the ribs all carry a different color, so they were defined in different shell properties within the Abacus input deck. They all have the same physical thickness, but they all have their own or independent shell definition. And if we run the algorithm to find weld sets by physical properties, limit will find separate welds for each weld position. So as you probably know, if you want to analyze welds within limit, you need a node set that describes the direction and the position of the weld, and you need the element rows connected to these elements. The simplest way to define these sets is to use the information on the physical properties of the shell. Okay, so I'm going to show all again, so the whole model is visible in the viewport, and I will run the generate weld sets by properties method. And what limit does is it will detect all possible welds, and a prefix PS property set and a ongoing number will define these sets. It's always a node set followed by the element sets, and that's how each weld position is defined. We can kind of change the visibility and scroll through the model just to see all the positions. There's one overall set that includes all nodes and all element sets. This can be used for the assessment type weld global, where we kind of analyze all possible welded elements in just one assessment run without defining the local details. But in this presentation, I'm going to talk about defining, doing a local weld assessment for each weld position. Okay, so we have all welds defined as node sets and element sets, and the next step is to switch to the setup manager. Open the setup manager, and now we can auto define all the setups, all the possible setups with one of these codes listed here. So in our case, I'm going to use a Eurocode 3 definition, and I'm going to select all the welds, possible welds that were detected by the property algorithm, and with apply I will get a large number of setups. They carry the same name as the weld sets, and what's interesting here is each of these setups connect to two different types of elements. So they're all like T joints, for example. The assignment is weld, that's what we need. It's Eurocode for the design code. And the status, this is important, is none. As long as the status is on none, you can't use these setups for assessment, and you can't select them in the job module. So you have to check and change the status to edited, which is done automatically if you open up this one setup and store it again. Yeah, it's just like a quality check. We don't want anybody to run a fatigue assessment without checking the setups. Now this is 22 setups. It's not a really large number, but still it might be interesting to see which of these possible weld setups has a status none and which has a status edited. This can be seen by coloring the structure by the status of the setup. And red means none, and as soon as I change a setup to edited, this will be green. So even in large complex structures, you can easily visualize which welds have been checked and which ones can be used for the fatigue analysis. Okay, now in our case we have these 6 internal ribs, and these ribs are connected to the rest of the structure by, let's say, double fillet welds. So what I can do is I can select all of these welds, all the welds between the ribs and the flange and the ribs and the web, and I can define their geometry and their FAT classes in one step. So this is done. I'll go back to color by all sets. Okay, so this is done by just selecting, first of all, selecting the welds that are topologically equal. I'm going to switch to the translucency mode, because then highlighted sets can be seen in a better way. So this is one of the setups we need, and this, so by just pressing the capital key and selecting, I can multi-select my setups. Okay, this is not needed. This is not needed. No. No. Okay, these setups again are connections between the weld and between the rib and the rest of the structure. Okay. So here we have all the welds selected. And they all have the same topology. They're all double-sided fillet welds. And what I can do now is I can just select one of these setups with the right mouse button, and I can, for example, do a multi-edit based on the PS005. So if I select this, then I get the following picture. So this is the setup mask for PS0005, and here I can define my weld definition, my weld geometry, and my FAT classes, and this is the weld in the structure. Actually, it's the one in the curved area of the beam. And for Eurocode 3 we have to define the yield stress, which is 355 for this material, and we have to define the weld type, in my case a double fillet weld with an A dimension of half the wall thickness. So I can define this as T times 0.5 for both sides, the top and the bottom side. And the D dimension is the distance between the mid surface of the shell or the sheet metal and the root, either the top or bottom root. So in the double-sided fillet weld, the D dimensions also are half the thickness. So this is what you need for a double-sided fillet weld. Now if I push the return button, we will get this picture here showing us a double-sided fillet weld. Yeah. So I'm not going to talk about the FAT classes used here. These are default values. What we could do is change the FAT class for the green shell on the P6 side, which is actually the non-welded side and should be a base material. So, and this would be FAT class of at least 100. So this is probably the better representation of our situation here. Okay, so this looks fine, and with apply I can close this window, and the status of all the selected setups changed from none to edited. Yeah. So if we check again using this color scheme, then we can see we have all the rib welds in green, and the longitudinal welds between the flange and the webs are still red because we haven't defined them yet. And just to make a quick check, I will, for example, check PS16. We can zoom into this weld, and it's defined as a double-sided fillet weld, just in the same way as we did it for the weld done here. Okay, so now I don't really know which weld number is connected to the longitudinal, so I again go into the setup manager. Okay, this is one of the lower longitudinal welds, and I will try to find the second one. Okay, so these two are both topologically equal. They again could be double-sided welded, so we could like have a welding sequence of first welding the webs to the flange, then introducing the ribs, and at the end closing it with the upper flange. Yeah? So the longitudinal welds on the lower side could be welded from both sides. That's what we're gonna do. Again, I'm going to select the multi-edit, and I will push the zoom button, and I will zoom in, and that's what I see here. I will define a double-sided full penetration weld for the blue part, which again is here T times 0.5 for both the top and bottom side, and I will leave the D values at 0. This was maybe too fast. Because I forgot the yield stress. But that's what it looks like. Again, we could change the P6 position to FAT class of 100, and we need the yield stress to define the welds here. Okay, so we've finished this. The next welds are the outer longitudinal welds, and this is simple because only two are left. So select those two, multi-edit, and in this case I would like to have a single-sided full penetration weld welded from the outside. In this case it's welded from the P6, that means it's welded from the top side. The weld dimension is T, and the D dimension is minus 0.5 times the thickness, and this is the symbol for a full penetration weld from one side. Again, we need yield stress of 355 for both element sets, and with apply we can finish this. Okay, so for a check, just to make sure that also the other side is welded from the right side, we can check the symbol, and this is correct. The reason why it's actually mirrored by the symmetry plane is that the shell normal of this web looks to the right, and the shell normal of this web looks to the left, so topologically both welds are similar. Okay, but in this case I think I forgot to set the P6 to 100, and I just wonder if we have it here. No, I think I forgot it. Apply. Let's check. Okay, fine. So all the setups are defined, 22 welds, just with actually defining in detail three setups or 3 welds on the structure. Okay, so if we want to make a fatigue analysis, we still need loads. In this case, I'm just going to import one load case, one bending load case, which was step 1 of my analysis, and I will create loads from that finite element result, and I will copy it, and I will change the sign to -1, so we will have a alternating bending moment on this structure. With dismiss, I can close the load manager. We can save it. The next step is to move to the job manager and to define or create a job. It's EC3 and multi-edit, just for the records, apply. The preferences actually defines which finite element code was used for the calculation of stresses and displacements. In my case, it's an Abacus ODB version 6.12.1. I'm going to use the English output. There's also a German output, but here the English one is selected. And my ODB file is somewhere down here. Multi-edit. Okay, which one was it? Probably this one. Okay. That's all we need up here, and here we can select all the setups we have defined, and we need the loads. And with apply, our job is defined. So I will save it before I start to run, and I'm just going to click on the run button, and limit will start in the background. And here is actually the window, which gives us an echo, what's happening. So we're still in the reading the data, and here we're going through we're assessing the single one by one welds. Actually, the main analysis has finished. We're writing results to the files, and here the text output is generated. And the job is done. So what we do here is we just mark the job and say view results, and then we'll get a picture with the degrees of utilization, max degree of utilization for the elements. That's what we get here. So the maximum degree of utilization in this case is 0.99, which would be permissible. So if I change the visibility to this translucency mode, then we can see all the welds, and yeah, the welds up here in the curved area show the largest degrees of utilization, which actually is clear because due to the curvature, the cross section of this beam doesn't show uniform stresses anymore. So we have local deflections in the cross section, which causes additional stresses in the welds, secondary bending stresses and whatever. So, but I will leave the interpretation up to you. So I'm at the end of my presentation. Just I hope this method and this way to define welds will help you in cases you're dealing with larger numbers of welds. And I want to thank for your attention and say goodbye.